Hi guys, today we're going to be talking about nickel, the element nickel, and the resource that we have taken out here in WA. So I'm going to start with I guess a little note that nickel really is actually one of the most abundant resources that we have on Earth. It's one of the most abundant elements that we have on Earth. However, we don't see it very commonly on the surface. And the main reason this is because most nickel, along with most of the iron on the Earth, is found in the Earth's core. I'll put found in the Earth's core. Why is that? Well, because it's quite dense, and early on in Earth's formation, most of those materials were pulled by gravity down to the center of the Earth. So, found in the Earth's core. When we find nickel on the surface, though, we find it in ultramafic rocks. So it's found in ultramafic rocks. And if you know any ultramafic rocks that we've maybe talked about in our classes, two examples are komatiite, and there's another one called peridotite. So ultramafic rocks, as you guys will know, if we think about Bowen's reaction series, they actually form in our very upper part of Bowen's reaction series, and they're made out of olivine and feldspar. They're also made at very, very high temperatures. If we think of high temps, we think of over 1,200 degrees Celsius. Now, ultramafic rocks can no longer form on Earth. Now, the question is why? Why can't we get ultramafic rocks on Earth anymore? Well, it's because the Earth is cooled. We can no longer reach those temperatures that actually create those rocks. Why is the Earth cooled? Well, this is a really good question, and it's one that's puzzled people for a long time. One of the main reasons the Earth's cooled is because we don't have those unstable isotopic elements that we used to. Uranium-236, uranium-237, that when they decay, they create energy and heat. Now, we still have those in rocks, but because the Earth is a lot older, we have a lot less of them. There's an opportunity for a little bit of reading on that there, if you're able to, guys. Have a look at why we, maybe some examples of radioactive isotopes, what causes radioactivity, and talk about the daughter and the parent and the daughter isotopes that come about from that. Okay, so we have less unstable isotopes which are not decaying and creating heat. Let's write that in. Okay, hope you can see that there. Sorry guys, I'm lacking a bit of colour today. So we know that the early Earth was a lot hotter. Primarily a lot of the rocks, some of the rocks that were formed were ultramafic rocks. Ultramafic rocks are formed at very high temperatures, and if we're and it's in those rocks that we find nickel. One interesting fact about komatiite is that it's actually, if we think about a rock that's being mafic, we might generally think it's going to be really dark, like a basalt or a gneiss. Sorry, not a gneiss, a gabbro. And those rocks, they are very dark. Those mafic rocks are dark. However, ultramafic rocks are very light coloured. And that's due to the lack of pyroxene and amphibole. All right, let's keep going. So we know now that we've got nickel and it appears in our ultramafic rocks. So let's talk a little bit how this happens. I'm just going to move that over a little bit as long as everyone can see. All right, so ultramafic rocks. I'm just going to label them as rocks. These guys are rich, they're very rich in metallic minerals. See that, there we go. So they're rich in metals, and if you look at the minerals and the composition of the minerals in ultramafic rocks, it becomes quite clear. If you compare the composition of the minerals of a mafic rock compared to a felsic rock, you'll see that there is a great deal more metallic minerals present in mafic rocks. Be something to look at. I'll just write that down. So this is a good way to think about a lot of our resources. Most of our resources that we find in mafic or ultramafic rocks. We find less in felsic rocks. Why? Well, it's really, again, due to Bowen's reaction series and what happens to those compositions and those compounds with prolonged heat and pressure. But most of our minerals and metals are going to be found in our mafic rocks. So let's keep going and let's continue. We want to think about, if we're thinking about these mafic rocks and where they come from, you might remember in past lessons we've talked about how these rocks will come directly from this magma will come directly from the asthenosphere, directly from deeper within the earth. Now, if we're bringing something up from deep within the earth, there are only a couple of places in the world where we can get these sort of rock formations occurring. One of them is hotspots. The other is divergent boundaries, if you look at places like Iceland. But hotspots is the example that we're going to. And many of our nickel deposits are actually thought to be ancient hotspot volcanoes. So we've got our hotspot volcano, and we are tapping magma that comes from deep within the earth, and we're bringing it to the surface. So that means this deposit really is a magmatic deposit. This resource is a magmatic resource. Okay. Okay, so the nickel comes from deep within the earth. At a location at about the asthenosphere. So we've got our hotspot, we've got our magma, and it's going to be rising up through the earth and forming our nickel deposits. It's going to be making an igneous intrusion. Now, if we think of different types of igneous intrusions that we know of sills, we know of dikes, we know of batholiths, and we know of laccoliths. Good. Okay, now let's look at how the actual nickel deposit starts to occur. I'm just going to turn the page. Okay, let's keep going and let's talk about the story about how a nickel deposit actually forms. So we understand that we've got very hot earth. We've got magma that comes from deep within the earth, around the asthenosphere, and we've got a much hotter earth. So we've got the possibility that the ultramafic rocks are going to form. So let's talk about now what happens within the magma. And I'll try and I guess we'll look at what we've got. So we've got high temps. We've got igneous intrusions. We've got ultramafic rocks. Cool. All right. So let's look at step one. Step one, within a magma body, and now we're talking deep within the earth, sulfide droplets will start to form and accumulate with each other. So I'll write this down, then we'll talk about what a sulfide is. So within a magma body, sulfide, and you can choose to spell it whichever way you want, with an F or a PH, it doesn't really matter. Droplets will form and accumulate. So sulfide is an anion. It's a negative ion. If we think about sulfur itself, sulfur has sulfide is S2 negative, and which makes it a negative ion. It's gained 2 electrons, so it's a sulfur atom that has gained 2 electrons, which makes it a negative ion, which makes it want to react with other metals and other minerals. So this is often why you find metals that are bonded with a sulfide, because it is this negative ion that attracts other metals. So let's write this down. So sulfide droplets merge and accumulate. These sulfide droplets merge and accumulate to form flow lines in the magma. So let's look at what this might look like. Let's draw a imaginary magma body deep within the earth, and then we might end up with something that looks a little bit like this. And we know the magma is quite possibly lower in density, so it's going to want to rise upwards. So these are our flow lines. All right, so remember I said sulfide is a negative ion. So what it wants to do is it wants to bond with a metal. So metals are attracted to sulfur. So let's go to 2. Nickel, copper, platinum, gold, the list goes on. Lead, let's put other metals. Are attracted to the sulfur droplets. And they stick to them. Nickel bonds with sulfur to become a nickel sulfide. You end up with copper sulfide. So these metals bond with that sulfur. Okay, and they flow. These metals join the sulfur on these flow lines within the magma. Okay. Next step. The magma then flows out of the earth, flows out as a lava. So let's see, step 3. When the magma reaches the surface, and I have to say becomes lava, so it becomes a lava flow, the sulfides will then sink to the bottom. Why do they sink to the bottom? Because they're dense. So let's say there's the surface. I haven't got any good pens today, but this pen will do. Let's say this is our lava flow. So our nickel deposit forms at the base of this lava flow. Okay, so because it's heavy, its density actually collects it together really nicely. Let's keep going. Step 4, the heavy sulfide deposits collect and pool at the bottom of these super hot komatiite lava flows. And sometimes it actually gets trapped. See that last little bit there? So what's interesting about this point here is just like rivers that flow and rivers cut channels, these lava flows will flow, and what will happen is a lot of the heavier deposits will get trapped at the very bottom of these flow lines and will often form in channels. And if I can draw another sample of one over here, sometimes you even see little depressions, little channel depressions, where lava flow will be sitting over the top, and just in these little channels we will have our nickel deposits. But what's important to know is that our nickel forms at the base of these lava flows. All right, let's keep going. Do I have room for 5 down here? Let's write this down here. Let's do 5 rather than waste another piece of paper. So in Kambalda, so if this is a little bit messy, geologists look for nickel deposits. In these channels. Another important word, I guess, to know is that the location between the base of the lava flow and the original country rock is called the basal contact. So the basal contact is what geologists are looking for. When they find a komatiite lava flow in Kambalda, they're not going to look at the top of it, they're going to go straight to the basal contact where the lava flow hits the country rock, whatever it might be. Okay. There is a little bit more we can talk about this, but I think we'll wait till we get back to school. That's it for now. If you've got any questions, email me. Thanks, guys.